is going to be for astronomy before the telescope. I tried responding in the comments on your video, but my comments aren't loading up, so I just thought I would create a video and I'll send you the link to this. But anybody that watches this, I would encourage them to come check out his work over here. My focus was on your work on Ptolemy here. Very much appreciate your efforts because it's helping me understand this very dense almagest that is a little complex for me to grasp, but really appreciate your work here. I just wanted to share something with you because I did find some similarities in the astrolabe. Now you're right in noting that the astrolabe, you're not going to find a drum for latitude 90, which would be all the way at the north central pole, and then the for your equator latitude, you can, the sliding scale allows you to basically it projects the different drum position based off of these 90 different latitudes that you could range from. So what this helps in doing is, again, I'm noting the position right here of the center of this ecliptic circle, and so you will notice that, like for instance, if I set this to 90-degree latitude, we'll see that this point right here is always going to be pointing to this same position. And so I got to thinking, what is special about the position that this is pointing to? So if we count the lines right here, what we can do is we can turn on we can highlight the equator and our tropic ranges to help us with this a little bit. But we'll notice that we're at 0 degrees latitude here, 23.5 north, 23.5 south. We'll see that the dimensions of these positions are not uniform. So these are condensed as you get towards the center. And if I take out a ruler and measure this on my screen, I see that this is 16 centimeters, 10 centimeters, and then 6 centimeters. So these are in a phi proportion, with 6 to 16 here being phi squared. And that'll be, I guess, kind of significant. But yeah, you'll see how this is being condensed as you get towards the center, these lines of latitude. But we'll measure this from 0 to 23.5 north. We see that this is then 25. So these are going to be in increments of 5. And we'll see that this is going to be then 30, 35, 40. And we see that the point is falling somewhere between 40 and 45. This is from latitude 90. So, and you're right in saying that this shouldn't be, the pivot point of this should be 66.5 degrees instead of 42.5. So this would be twice the distance then. It's pointing to a point that's twice the distance from the center than just that one increment. Now if we wanted to check this, obviously the reference lines are going to get kind of strange as we shift the center, these two centers apart from each other. So if we're going to look at latitude 0, for instance, we'll see that the points here are going to be, they're going to be off a little bit. So if we move this back, let's move this back a few minutes so that we can kind of get an idea of where that pointer is pointing to on the reference line. So we'll see that here again we're at 0, 23.5. Now the lines relative to the center here are going to be 23.5 latitude. This would be 20, or this would be 30 then, right? Because we're going to be 10, 20, not quite halfway. So that 23.5, this is, we're counting by 10. So this is 30, 40, and we would see that the pointer now is going to be, again, about a quarter of the way between 40 and 50 right here. So again, we're pointing at 42.5 degrees, but we won't notice if we reverse this. We'll see that pointer, we don't really have a reference line to go off of because it's transitioning between these two grids. It's going from the grid, the center grid here, to the grid relative to the equator grid right here. So if we stop it and are going to look in this position, and again we're gonna take our reference to what we're referencing to here. This is again the equator. This would be 23.5 degree a circle, which would make this 25. So again, we're counting by fives from this location. And so this would be, again, 25. This would be 30, 35, 40. And again, we're pointing to this 42.5 degree mark. So this is what I'm pointing out with the astrolabes. Obviously, I'm referencing this tool as a part from the what do you call it? The physical tool that you would get that would only have one of these drums. But yeah, again, it's just kind of interesting. You see how these points are always going to be fixed to the stars. So it appears that this sort of ring is always going to be centered on this one latitude, is what I was pointing out. And that's why it's interesting looking at your work on Ptolemy, because, if I were to come over and let's say I created this sort of diagram here, and I'm building this off of the biblical numbers. So if I go in the book of Numbers and I'm looking at the breakups, what I find is that the quarter part of Israel right here, that what it gives you is this 151,450 in the first census. This is the 90 degree piece that you would set this to. And that's going to be the combination of Reuben, Simeon, and Gad. And then you're going to find that there's this other piece missing from Levi. But what happens when you do this is you'll find that Judah gets pushed past 90 degrees right here by this particular amount. And then so the remainder of Judah, of this Judah South position, is going to be this right here, 39,650. And when we put this up to degrees of a circle, just as 151,450 is going to be 90 degrees, you'll see that 39,650 ends up being this 23.5 degrees. And this is significant. For one, it's pointing to this ecliptic range, but it's also showing us that this is relative to phi squared times 9. So if we were to look at the, sort of the relationship of this value and divide this, if I were to take and divide this value right here by 9, we'll see that it's, that's phi squared. Okay, so if we took the square root of this number, we'll see that it's showing us that it's relative to phi again. And so what you do then is that you can assign that to the analemma. The analemma breakup, the crossing happens at 9 degree north, and since we're at multiples of 9, we can break the analemma down into proportions, dimensions, relative to the number that we're given from the biblical account. And then so now we got, basically our radius right here, this 90 degree radius, will be our 151,450, and then our range right here, our tropical ranges will be 39,650 or 79,300, which would be the total range here. And you find a lot of these sort of relative measurements in miles when you get into Stonehenge and squaring the circle and a lot of these other things. So you're going to find, regardless of the metrology, you'll find, values they're sort of correlating. But, Ptolemy is interesting because he's using, like, for instance, his when we talk about pi, the modern formula for pi is this value that we're going to get. But, the basic understanding, when you're going to use this as a framer or something or construction, you might just use a 22/7, which would be the quick field expedient method, right? The most accurate would be this 355 divided by 113, but Ptolemy, when he does his parts, he's doing 60 parts, and then he finds that the perimeter of the circle would be 377. So this is his value. Of course, he doesn't recognize that this is a Fibonacci number. We know that the Fibonacci and Lucas numbers are tied to square root of 5 and the golden mean and all this other kind of stuff. So at any rate, the approximation for pi that I'm using is going to be, since we're dealing with 233, we find that 151,450, this quarter of the circle, is going to be relative to 233. So all of these values you'll find will have a least common multiple of 65, which you can draw out. These will be all the factors for all of the values that you find right here. But so at any rate, I would use this value for my pi. So when I take the radius and I multiply it by pi, I'll find that this value divided by 233 times 732 is going to be this value right here. This value happens to be 39,650 times 12. And of course, 12 and pi are relative. We can divide pi by 12 to get, our phi squared divided by 10 value. We can also take 42. You'll see that there's 42 stops for these positions. I won't get into that here, but anyway, you divide 42 by pi, you're going to get this value here, which is going to be the ratio of the sun to moon, the sun to the moon sidereal value, and then if you subtract 1 from this, you're going to get the sun to the moon synodic value. And of course, we see this in the 19-year cycle, with the 19 being the difference between 235 and 254 and all that kind of stuff. So this is, I guess probably understood, or, I guess maybe that connection isn't made. But again, I just wanted to point out the nature of this right here, because the deferent, Ptolemy's 60 parts, he calculates that deferent to 10.3, or 10 and a third, which would be this value right here, 26,000, which happens to be, I'm already seeing that this is the, when you go to the next census, Levi's 2250 becomes 4070, which when you multiply this by phi, again, that's going to be 6585 and a third. That's going to be your ecliptic days between eclipses. But this 13, you're going to see that this movement happens by 13,000. And we also know that 26, the Yod He Vav He, all that kind of stuff, but people probably understand and know. But the 26,000 right here, if you multiply 233 times 2600, you multiply that Fibonacci sequence by 2600, you're gonna arrive to this total value right here, the 605800. So I found that was interesting with that if you convert that 60 to 10 and a third, you're going to arrive to this value of 2600 as the deferent for the moon. And that you get a lot of interesting values when you do that. So I just put these on a line right here, and I did the breakup from the tropics to the equator, all based off of this value that I've been given in the Bible. And then you'll find that all of these values have a least common multiple of 65, and you can break them all down. But again, this should be, if you just shifted this ring right here. So this is what I did, was I just created these are the same size rings. So your equator and your ecliptic, and I shifted this over so that this circle should fall on your two tropics right here, and the center of that point would be the same distance as your tropic. However, the observed is going to be twice that distance, right? That 42.5 that we find in the astrolabe, the apparent center of this is going to be twice that distance. So if we double that distance from latitude 23.5 from latitude 90 north is going to get us to 66.4 degrees north latitude here. So at Z right here would be double the distance. That puts us at 42.87 degrees north. So there's something going on with this apparent position, and then there's something going on with the construct of the astrolabe, of how they're using phi to condense these two pivot points. So you're going to basically take this point, and you're just going to stretch it and put Z over A, and then it's going to stretch the ratio, the proportions of these into phi to 1 all the way down when you do that. So something's going on with that. This deferent for the moon, again, was very interesting because it puts that at this 2600. Very, very interesting numbers start popping up. I couldn't find the 2.5 value that was shown from the first instance, but you do find some interesting things. Like if I go and look at a Fibonacci square, for instance, and you're going to look at how the center of these squares fall on two different lines, essentially from your origin block. Depending on how you grow it, this will be different, but this angle isn't quite that 24.5. This ends up being an 18-degree angle, I think. So it doesn't quite line up unless you'd have to index it or something. But I thought it was pretty interesting, some of that stuff that you had up there. But at any rate, that's what I was getting at with the astrolabe. Hopefully that helps. Yeah, I'll be looking forward to all the work that you do in the future. I really appreciate what you do. So thanks again, and we'll be seeing you.